everyone. We're gonna start. Thanks for joining. I think there are still pizza left, so we can probably have a chance to grab a pizza slice. It runs quite fast. So um, anyway, welcome to AI/ML Conversations Meetup. That's our monthly meeting where we talk about ML. And this time we're gonna have a part 2 of our September meetup. So who have not scanned this code and check the slides, I very strongly encourage because it makes much easier to kind of tag along with today's speakers. So please, if you haven't scanned this, there's the links, and if it doesn't work, you can come closer. I want to talk a little bit, like for one who is here first time, I want to give a few words about what is AML conversation. This is a meetup that born from a group of people who journey over the drink and talking about AI and ML. We kind of decided that why not to bring those conversations to some kind of higher level and give a venue and like a stage for one who can share, who can share their knowledge and experience in the field. So that's how this event born, and we really want to encourage people to become one of our speakers. So yeah, so this meetup is primarily about people coming over and sharing their knowledge, experience from academia, industry, research, startup. Kind of the AI got crazy, and the idea we want to be kind of help each other to understand it. When you understand complex thing, you can build it, and hopefully you can all make the world a little bit a better place. And so if you have some topic to share, here's a link. And a few words about organizers. Myself, Vlad Ermin, I am Hori. We are a host here. So if you have any questions, suggestions, feel free to reach out to us, ping us on Discord, LinkedIn, Instagram. We always open the chat. We have a code of conduct here, so try to make this event and this place like comfortable and safe for everyone. So if you feel that something is going off, please immediately reach out to one of our organizers, and they'll definitely take action. A few housekeeping stuff. The restrooms are like the latest restrooms is all over the hallway over there, right? And the men all to the left. You can stay in touch with that. We have like a Discord. We also run some like online events, and Discord is our place where we like communicate and talk about the topics and kind of ask people what topics they want to cover. So there's like a good place where you can give your feedback and also like chat about potential speech on our future events. So for the ones who join us from Supermamas, there's a QR code you can scan right now. Also, you have printed QR codes all around the room. So if you missed this one, you can find somewhere here. This is also important part. Since AML conversation born from just casual meetup in the bar, we kind of want to follow along with this tradition, and every time after this official part, we meet in the Old Town Fair, a few blocks away from here. So feel free to join. And I'll put the link after the event on the big screen. So with that being said, I will pass the the mic to my co-host to talk about Capital One, who is our sponsor. This event won't be possible without it.
Hello, my name's Ian. I work here at Capital One. Capital One has been fortunate enough to sponsor us for this event. They covered our pizza and the location. In turn, Capital One is looking to hire for AI and machine learning roles. And because you showed up here, that means I can get you an in on this whole process through referrals. If you are interested in working at Capital One, having a nice work-life balance, pretty good pay, in my opinion, there are QR codes there and all the way in the back too, that have more details on like how to go through the referral process. First step would be to email me, and then we can go from there. We got a great show for you tonight. We got two ML people who are going to be presenting for us. The first will be Shafik, who will be talking about this multimodal machine learning. And later tonight, we'll also have an India to talk about vision transformers. So I'll go ahead and let me take off applause here for our first speaker tonight.
Welcome to my talk on multimodal machine learning, part 2. This is a long subject, and the last time that I talked about it, I was able to kind of get to, if I recall, the machine learning part on some level, but there was a lot to discuss, and so what I decided to do is like make a part 2 of this and go a little bit more into some of the application level stuff, but still stay, balanced in the machine learning concepts that are relevant without getting too inundating about what I want to discuss, because as everyone knows at this point, who are familiar with multimodal machine learning, it's pretty much multimodal applications are the crux of AI at this point. Everything is able to ingest images now. All the foundational models are able to ingest video in some cases, produce images, produce video, do search based on images and video and audio. And so we're past the world of just pure LLMs and text-based models. So essentially, there's a lot in the multimodal case is much more complicated in general. And so it's a little less approachable in my opinion, but it's again foundational to understand how it works and the principles that are present there, because they combine pretty much all of the different ways that we input data and into our own consciousness and into our own ideas and into our own way of speaking. And it actually, if you're one of the proponents of the people who are very interested in how AI will advance to something like AGI or something like that, it will pretty likely be through the multimodal path. Okay, so this is just like a rough outline of what I'll be discussing. I've broken it down into sections. So I'm going to just start again where I left off with the actual models themselves. I'm not going to go too deep into the models or the mathematics, because I want to get to some of the actual demo implementations of things, which I will try to demonstrate. So we'll start with like the basics, and then I'll go into multimodal RAG, which is pretty much one of the main ways that people use LLMs or any sort of foundational model these days. They interact with it through wanting to search and wanting to retrieve information and produce an output using multiple different kinds of inputs. And then I'll go into some other more esoteric things, not too deep, but we'll see what we have time for. So as I recall where I left off last time, I was talking about the different ways that fusion occurs. Recall in multimodal models, the multimodal architecture requires that you actually fuse cross-modal information. So if you have vision information, sound information, if you have other depth information, there's many other kinds of modalities. You need to essentially combine them in different ways in order to achieve machine learning, the appropriate kind of machine learning that can truly extract the context that you need from a multimodal system or architecture. So just quickly going over some of the ways that the data is fused, the typical strategies is the most common one is called early fusion, where all the features of the different modalities are integrated. They are integrated, and then they are fed to a machine learning model. The example that I have here is all these bagged words, these different features, vectors that are from different same text inputs. They're bagged words, 2 grams, etc. Machine learning is, fusion is done, and then the SVM, support vector machine classifier, is applied, and then you have some result. In the second case, you have, well, I'll go into that in a second. So early fusion is good for a lot of things because it allows combination and then learning on the data, so you actually capture a combined stream of input, and the sort of the drawback of this is that the model that has to be used to understand the data as it's fused together in an early context is actually fairly complicated than the alternative, which is late fusion, which means in late fusion, I take each of my features and I do machine learning on them first. So as you can see, there's a SVM attached to each of these feature sets, and then the final learned output is then fused together in the context of late fusion. And so late fusion is good in scenarios where you have a lot of different data that you need to reduce pretty fast. You need to do the learning on early because the model can get way too complicated. So this is sort of the way that you can simplify the final result. There's drawbacks between the late fusion operation in that the complexity of interactions is reduced on your final machine learning model, and you lose some of the potential interesting cross-modal interactions. That's just a refresher on what the fusion stages are. Just remember, fusing is the combining of the data. So we'll start with the first ideas, like we talked about autoencoders. So everyone is familiar with an autoencoder, I presume. Right. Okay, so an autoencoder is probably one of the most basic machine learning encoder models, which basically takes in information, some sort of feature, compresses that to the latent space, the embedded latent space of the machine learning architecture, and then the decoder outputs the same input that was encoded into the latent space. So as you can see, I have this handwritten 2 from the end of this data set. It was encoded into the latent space, and the decoder produced a 2. It's like a mirror, pretty simple, straightforward model. It's an unsupervised learning model, and that's a key thing to the way this applies to fusion later. And it's useful for the autoencoder. Basic autoencoder is used for a lot of different tasks, including noise cancellation or noise elimination, or creation of clean data sets for pre-training other neural networks. And then, as many people probably know, the variational autoencoder, variant of the autoencoder, was one of the first useful generative AIs out there. So the autoencoder / VAE are actually both simple generative models. And so on the right, we have the diagram of the autoencoder. It's just basically 2 neural networks connected together, fully connected neural networks, and an output. So that leads to the concept of the deep correlational autoencoder. I also briefly touched on this before, but the deep correlational autoencoder is an advancement of the autoencoder architecture, which allows for multimodal machine learning. It's technically actually not the cutting edge model or architecture, but it's worth going over because the way it kind of does machine learning and multimodal machine learning is fairly intuitive once you understand the process of what happens. So it combines the principles of deep learning, again, 2 neural networks, and it applies the principle of canonical correlational analysis, CCA. And so what CCA is in probability theory, if you are trying to correlate 2 sets of variables together, you can find out a reduced set of values or a weighted set of values which represents the optimal correlation between 2 sets of input. That's what this model essentially does. Just a quick example, if you take, for example, heartbeat, if you take heart rate data, if you take blood pressure data, cholesterol data, then you try to correlate that with weight data, height data, and some other variable that's related to physiology. Then the resultant correlation is the optimal relationship between the 2 data sets. And that's that's essentially a linear combination. The deep correlational autoencoder uses the same principle, except because they're neural networks, they're nonlinear in nature, and they're able to learn more complex relationships. So again, nonlinear because the neural network nodes contain activation functions, nonlinear activation functions. So the way, once the correlation occurs, the correlation process occurs, and we can go deeper into that later, you have the idea of minimizing the loss function, as any neural network does, but as I mentioned last time, the loss functions that we're trying to minimize are essentially correlational loss. We're trying to maximize the correlation between two different modalities. So you can think of the autoencoder on the left having input modality A and an input modality B. These input modalities could be like voice and sound, and they could be misaligned. Let's say somebody's speaking, right, in speech, and once they're essentially fed into the autoencoder model, the model trains them, then the end result is that these are combined into the shared latent space. The combination into the shared latent space via training is essentially the process of minimizing the correlational loss. And meaning once the autoencoders uncompress their data, because that's what autoencoders do, the end result is that two things are synchronized. So the lip motion is synchronized with the voice motion, or the lip motion is synchronized with the voice. So you can think of alignment of modalities as being one thing DCAEs do well. And then the real challenge with this model is that making sure that the alignment occurs and that you're maximizing correlation between the models at the correct, between the modalities at the correct points. So making sure the lip sync is done appropriately with the visual, the voice output. And so I'll leave the paper that goes into that, but really the transformer model, everybody knows, has pretty much dominated the machine learning landscape for the longest time, and all of the like linear multimodal models use the idea of cross-modal transformers these days. So a cross-modal, everyone is familiar with the transformer model, right, at this point. Has anybody ever looked into cross-modal transformers before? Familiar? Okay, so essentially cross-modal transformer is essentially a set of multiple transformers that are paired together. And what they do is that they take in data from each of the modalities, for example, sound and audio and visual, and then they will apply cross-attention to each of the input modalities. So, and I'm summarizing briefly here for the segment of time, for the sake of time. But essentially, if you're familiar how attention works, self-attention works, cross-attention works similarly in the sense, except that the query key value vectors between the two modalities are compared against each other. Essentially, the end result is a similarity function is applied, and finally, an output is produced and as it goes through the different layers of the transformer model, and that output is essentially the correlated version of the two inputs. So they're used all over they're used in every model you can think of. Some of the models we'll talk about later. Foundational multimodal models are using them now. And they, again, they're very scalable, and the scaling laws apply to transformers. That's why it's very easy to create more advanced multimodal systems using a cross-modal transformer. Not so easier with other systems because the same scaling laws don't apply as in the same fashion. And so again, they're good for a lot of different things, which I will attempt to demonstrate. So this is just a quick slide on the different types of fusion operations. And the reason I'm bringing this out is not to go into necessarily the mathematics of it, but just demonstrate that fusion becomes extraordinarily complicated from a data perspective. So you can do basic linear fusion by adding two modalities together. That's sound and voice. You'll get some level of shared intelligence that you can extract, but a lot is lost if you're only doing simple linear operations. So the scale and the order of the operations increase such that I'm doing things like multiplying things together. You get multiplicative interactions. At some point, you'll have to use tensor operations to combine the two modalities together in a more complex way. So you have all the tensor relationships in multiple directions. And then finally, when you're combining everything together in the most complicated way, you get something known as high-order polynomial fusion. What this means, the reason I'm showing you this is because, again, the terms, the order of the terms increases so much that you're essentially suffering from the curse of dimensionality. And your data becomes sort of untenable until you do things like optimizing the fusion techniques. So if you've heard of dimensionality reduction, obviously everyone's heard of like PCA and whatnot. Drawing an analogy to that, in multimodal fusion operations, you have something called low-rank fusion techniques. So basically, because this is all essentially matrix interaction, low-rank fusion techniques rely on the matrix interaction between two models having a low-rank representation that captures most of the relevant information to the. I'm also going to assume people are familiar with low-rank operations here. You're familiar with matrix mathematics. If not, well, if not, then it just means that there's an operation that produces a matrix that has most of the similar information to your high-rank, high-dimensional matrix. And so that's great because then, because of this property, you're able to create a much more efficient multimodal model, which can capture a lot of the same information. So it's essentially like compression. So there's a lot of different techniques, and embedded in a lot of these transformer models and other multimodal models, things like singular value decomposition and other techniques are used to do this low-rank operation. And there's many other types of operations which essentially reduce the dimensionality, but this is a very common one because, again, it's on the matrix level and it's fairly easy to implement into our machine learning neural network architecture as a stage. And so long-range fusion is applied in all sorts of systems as a stage because, again, the dimensionality of all practical systems goes up quite significantly, and so you'll have to apply that all over the place. So, multimodal RAG. Everyone's familiar with RAG, retrieval augmented generation. And so if you've used ChatGPT and asked for internet searches, you know what RAG is. If you've ever fed an image to ChatGPT and asked for some text associated with that image and a result to return based on those inputs, then you're doing multimodal RAG. So you're doing essentially augmented retrieval on all kinds of input. And I'll go back and I'll go into that a little more in a bit. But you have the point, now it's a very complex thing overall because multimodal RAG involves a lot of stages. It involves good annotation of data that's you're fetching and retrieving, right? It's not just all magic. In many cases, you have complex systems which attempt to find good relationships between image and text data upstream before your RAG component ingests the data. But it's not all, it's actually quite involved process overall, but it's used in pretty much any kind of like multimodal system these days, and it's one of the most useful techniques of multimodal machine learning. So, some of the techniques which are using multimodal RAG are visual question answering, VQA, things like outputs, captions, captioning text, you name it, image generation, image retrieval, image understanding. They're all, and what I'm going to be, and so like I listed here a few common multimodal RAG systems, right? And so everyone is familiar with CLIP, how that works, I presume. I did talk about it in the last talk. There's Florence and Flamingo are two models that have come out recently, fairly recently, competitive models by Google and Microsoft that essentially are, they're not open source, but they've been trained on lots of data, a ton of data, and they're essentially competitive in which model performs better for different benchmarks in evaluating multimodal models. And then you of course have DALL-E as well. So I'm getting through this a little because I want to get to the functional demos that I have. So you've heard of CLIP, has anyone heard of BLIP before? Okay, cool. So if you're familiar with this space, BLIP is it's an advancement over, well, I would call it an advancement over CLIP that was built by Salesforce. That is, I think, overall, it's much more effective in describing context when it comes to a retrieval task. So it is able to, so basically what BLIP does, it does a few things different than CLIP, but one of the things that it does is that the B stands for bootstrap. So the BLIP model will generate in a set of predictions, estimations, outputs, and it will then reuse those predictions and outputs as its input to refine, again, further refine its output. So this process of repeated refinement that BLIP does is actually been found to be quite effective in contrast and in comparison to using labeled data that for example, Clip is using, that is purely labeled and not generated and refed into the system. So again, I mentioned it has this is just generally the overall high-level architecture. And so again, what it can do is image captioning. Let me see if I can get quickly to the demo. So here's my demo of Blip. Let's see. And so this is just some steps on how to do this in Python. One thing I want to do with these demos is that my intent is to demonstrate ways that you can implement these yourself, because I think it's cool that people can actually do this in open source manners. So this is
So we today have a demo on using Blip for alt text generation for images. Normally, when you have image data, you have alt text that is edited by people and added to the image to describe the image in natural language. And this normally takes manual intervention because a person has to not only describe the scene, but describe what appears to be happening in the scene and in a particular style and format.
So this might be hard to listen to a little bit, but what I'm going to do, I'm just going to skip to the parts to see to demonstrate what it's doing. So if I run this here, and this, a couple walking down the street holding balloons. Notice, okay, sorry. So basically, the tool that I built, you load in. What's that?
That's walking down the street holding balloons. So notice how contextual this is, right? This describes the scene itself and describes the people, not just as individuals, but as what it appears to be, that they are a couple and that the person is holding balloons. So it's not just listing out objects, it's describing the...
So this is my tool that I built to take in an image and then actually give it in alt text, right? And so notice that it's the alt text is actually quite varied. So for example, I can actually demo the tool again, but in its own server that I set up as opposed to Colab.
One more time.
And so I pick another image. So that's actually pretty good if you think about it for a non-foundational model that has a limited set of training. Remember, this is all installed on your machine with pre-trained data that comes from the Salesforce data set. So again, this is not using any API or anything like that. You can just run this off, a small processor at this point. And so, to me, that's fascinating because that means the ubiquity of machine learning is becoming, advanced techniques is actually becoming very, very vast. So, and again, there's more complexity with this model, but I want to show you some other techniques. So Blip was great, but then Blip 2 came along. And now Blip 2 is essentially a multi-stage version of Blip that does even more advanced stuff than the older Blip model. And it uses, what's interesting is called, the core part of Blip that differs from Blip 2 that differs from the first Blip is this idea of the Q-former. And the Q-former, or the querying transformer stage, what it does, it is actually trained to ask questions to the model. Almost as a person does. It will ask questions to the machine learning model in the latent space. So it asks questions like, if you want to, for example, if I put the dog with the bite image and I feed it into the model, it will start asking things sort of generatively about what's in the picture. Is there a bike in the picture? Is there a dog in the picture? Where's the dog in reference to the bike? Now this is actually quite mysterious because it's this is not a human asking questions. The way a convolutional neural net works and understands images is through a feature space that it constructs from image layers. This is the same thing. The questions are not human questions. These are embedded questions in the model, which help the machine learning model understand. And then when you ask questions to the model, which I'll demonstrate in a second, you'll get to see that those questions correlate to these embedded questions that the machine learning model learns and you are able to interrogate an image in a very powerful way by having this setup. So again, the Blip 2 again leverages pre-trained language models, and it has zero-shot learning. Many of these models are now zero-shot capable, so they don't have to be trained on the data that they were originally the exact images that they're trying to look at. They can learn from the embedded space alone of things that they've already been trained on things that they've never seen. So that's what zero shot is. And you can actually connect Blip to an LLM if you want, and you can produce actually very varied output. Now let me just demo Blip 2 in action. And actually, I'm going to, can you see my screen? Yeah, you should be able to see my screen. Okay, now, here's my Blip 2 model. I have this actually in the server running. Okay, so let me try asking a question. Let's see, what is this picture about? A couple holding balloons in the street. Okay. What is the road made out of? Cobblestone. It has very nuanced questions. What is the coat? What colors are the balloon? Pink and white. Again, this is all embedded in the model, no APIs. Okay, this is all that you build on your machine computationally. You actually have the code for the model there. You can modify the code. You can, in fact, if you want to inspect the transformer layer, you can do that yourself and play around with the actual layers and make this model do some crazy things, all on your own machine. Again, fascinating to me. Okay, so installation steps here, if you want to play around with that. Now, who's ever heard of ImageBind before? Okay. All right, so now we're running into some very odd territory. So ImageBind is a framework by Meta. And a lot of interesting frameworks have been built by Meta. But when we talk about image retrieval, sound retrieval, RAG, multimodal RAG, we're usually thinking about audio, we're thinking about text, we're thinking about images. But what's interesting is that the ImageBind framework, which came out in 2023, allows you to obtain data from 6 different modalities into a unified model. Now, what are 6 modalities? What could they possibly be? We'll get that in a second. So, again, it's powerful in the zero-shot and few-shot classification case. That's important for all the models. But it allows, this is the key thing, this allows new emergent possibilities for cross-modal information retrieval and content generation. For example, if I put in an image, it can actually generate the audio for that image. If I put an image of a submarine, right, and it understands depth data, it can predict how deep the submarine is based on the image. So this is the interesting thing. There's modalities that ImageBind deals with are things like depth, accelerometer data, temperature data, video, audio, sound, and it can do essentially retrieval in all of these modalities. So I'll show you an example. This is from the ImageBind site. Okay, so this one is just compiling on its own.
Okay, so we're going to talk quickly about ImageBind. So here's an example from the ImageBind site where we can combine different text, different sound and different images to get different outputs. Okay, so let's say we start with a dog barking. And then we click on this image of this beach here, and so it retrieves a dog on a beach. Okay, so if we have pouring, the sound of pouring, and then we click on here, the apple, automatically the system generates a faucet with apples and water pouring on the apples. Now this could be generated or this could be actually pulled. That's an interest. You can choose to do either of them actually. And then let's say we have a car engine, and we click on the image of a beach, then we have an image of a truck on a beach. So lots of
again, kind of fascinating because those are now systems that are again can run on your machine, right? There are no APIs required for large foundational models, and you can probably discover emergent associations on your own if you run ImageBind locally and try that out. What's interesting is that some people suspect that something like this is actually a fundamental component of AGI again, when emergent retrieval occurs and emergent association occurs. I'll get to your question in a minute. I want to get through all the stuff that I'm doing. Okay, so I'm going to talk about a little bit about some advanced multimodal techniques. So is anybody familiar with like video analysis, video understanding? Okay, so video understanding is the ability of a machine learning model to understand video, right? Not just a single static image, but the ability to understand motion in the video. Most of the models that allow this or allow for this use a principle of optical flow, which means they're able to look at images and between frames, they're able to interpolate the direction of motion between frames. And the machine learning actually occurs on the direction of motion between frames. So this is an example of a ball moving through a video, and that's the optical flow vectors are constructed as the ball moves, as the image occurs. And optical flow in classical image understanding and video understanding is used for action recognition and tracking movements. So combining with CNNs and two-stream networks, you can actually do machine learning here to find out things like prediction on where the ball is going to go, and also what's happening in the image. So everyone's familiar with the convolutional neural network. Has anyone ever heard of the 3D convolutional neural network or inflated? Okay, so this is a much more advanced version of the standard convolutional neural net, which takes time as a dimension as well as height and width. And what you can do, in the same way that standard convolutional neural net, if you learn features from an image space, you can learn features from a time, height, and width dimensional space. So time itself is has learnable features, which are important to video understanding. And these models have been successful in action detection. And I'll demonstrate too. I have a thing there too. And so in order to train these models, you have the kinetics data set. There's the kinetics 400, 500, 600, and 700 data set. And the number the number that is associated with the kinetics data set is the number of actions that this model can be trained to understand. So here's my demo on this. And I also have this on a server that I built. Here, okay, so let's say I have some videos. Okay, let's say I pick a video, and upload. And so what the model should do, it's able to understand what's going on in this video. Let's play the video. So as you can see, the person is about to kick a soccer ball. So it has some probabilities of things which it doesn't, it's guessing, but the highest probabilities seem to be correct. I'm not sure what POI is, but I know this is soccer, right? So let's say I pick another video. So I put this. And this is the front end that I built for the back end that I built that uses this 3D convolutional neural net model. So as you can see, this person is swimming in this lane, and this is just a video I picked from the internet. It can be any video, it doesn't matter, like whatever. It can even go down to the particular types of strokes that is happening in this video, right? So breaststroke, butterfly stroke, and a low probability of bobsledding, but whatever, I mean. And let's go to another video. Again, random videos I picked just for this, from the internet. No annotations, no metadata in the video. This is just learning on what's happening in the video. And so it thinks that it's almost 100% chance that the person is playing tennis, that the people are playing tennis, and there's other probabilities associated with this. Sometimes the model, depending on how you train it, now this is just a simple version of the model that I built, so if there's some like weirdly complex stuff happening in the model, it will not necessarily understand. So this is just like, people like dancing randomly in the street. I just took this random clip, and so this is like people doing funny dances. But like, it thinks it's like all this other stuff, paintball, fighting, kicking, headbutting. But I mean, it kind of looks like it could be, anyway. So, back to the presentation. Oh my goodness, what's going on? Okay, so another interesting multimodal model is called stereoscopic autoencoder. So you know how autoencoders work, that you take in images and then you can output another copy of the image. The stereoscopic autoencoder takes in depth data as well as image data. And what you can do is you can put in an image of something oriented in a particular way and create a completely different orientation of that output. So this chair that you input can be turned in another direction. without like knowing anything about it. It only is fed the chair itself and depth data. So again, the way this works is that the data is encoded into a 3D latent space because you have depth associated with it. And then you reconstruct 3D as the output at a different angle. So what's interesting about these models is that you can use them for things like VR animation, 3D animation, creating 3D, all sorts of 3D models, and you don't have to render the thing from scratch. You can just create something like this person in this different orientation just by feeding in a few representative images. And if you're familiar with the neural radiance fields, NERFs, this is one way that NERFs can actually be constructed through the use of stereoscopic autoencoding and other types of techniques. And so if you're familiar with Whisper, Whisper is not a multimodal model, but it's a sound-based model. So it's a transcription model where you take in data and then you can transcribe it to any kind of output that you want. So for example, if you take in someone speaking in English.
The lazy brown dogs jumped
Over the cow.
over the cow.
Okay, so, and then that was me talking, and I stuttered.
Le chien brun paresseux saute par-dessus la vache.
And so that's the model just translating something to French directly. So the interesting thing about this is that you've seen like you've seen MetaConnect, you've seen all these like trade shows that have like the models being able to produce advanced outputs. So again, I like showing like the pieces that can be used to reconstruct something like that. So if you wanted to create your own MetaConnect Ray-Ban or whatever that translates reels automatically, I mean, here's a start, right? So almost to the end. Everybody has heard of wave to lip before. Okay, so the reason I brought up all the stuff with video is that because it's interesting. Generative adversarial networks, which is something people should be familiar with here in general, is a type of net. I have a whole discussion about those, but essentially it's a way. It is the generative AI that came before diffusion models. It's still used in many contexts, and it's a very powerful. Very powerful machine learning model that's usually used to generate things like deepfakes. One thing is that there's now multimodal frameworks built on generative adversarial networks. The Wave to Lip framework is a framework that came out in 2020, I believe. And what it does, it allows you to synchronize lip motion with sound data. And so you'll see an example of that in a second. So you can actually alter one photo and change the lips moving of the photo based on a driving video. And a lot of the news about deepfakes and other situations that occur where people are cloning other people through voice cloning and through avatar generation occur through using a framework like Wave to Lip. It's neural voice cloning. And so, and you can actually use Wave to Lip for legitimate purposes. For example, like translating actual speech into other languages. So if you're speaking to somebody and it's not a native language, you can have them respond to you and just watch the lip motion. It's very interesting overall. I'm not going to go to the depth of it, but here's my little demo that I did.
Trump is doing the most amazing things with generative AI. He's not only the greatest president, but he's also the greatest data scientist. He's making AI great again, okay? Ask Shafik Quoraishee.
So that's my favorite video. And again, this is a fake. You never said that. But I don't know, maybe you will. Essentially, the way that I built this was the hard way of doing deepfakes. At one point, you take in lots of training data, you attempt to compress the data, you use a neural voice encoder, and then you match that using like Wave to Lip to the actual video, the driving video, and then the lips move according to the sound. And if you look closely, you can see it's a little blurry, but this is, again, I did this last year, or early in the year, whatever. The technology has gotten much more advanced, but again, for learning, this is great. And here's an example.
But life cannot just be about solving one miserable problem after another. That can't be the only thing. There need to be things that inspire you, that make you glad to wake up in the morning and be part of humanity. That's why we did this.
Okay, so there you go. And that's been my presentation. I just wanted to leave off with some advanced version of the voice cloning and how essentially that is like the pinnacle of how multimodal is applied now in other ways besides multimodal RAG. And here's some resources if you're interested based on the models that I put here. Again, this can all be run in code if you want. And yeah, I have the papers are all there in case you want to dig into what's going on with this. So.
Okay, we can take a few questions.
Hey, do you think? Hey, so, excuse me, my name's Chris, by the way, but so if you were to like use, say, like a what if / as if loop, I'm very told and stuff. But if you were to use like a loop, maybe of like contradicting questions, maybe like base data really, say in each section of this, and have the AI really test itself rather than have something else talk to it, where it's constantly questioning itself in this loop. At each set, at each point in this, wouldn't that overall increase the accuracy and maybe even the speed? Did I even explain that well?
So if I can understand, are you talking about in the video question answering?
Actually, every step, like say to start from the beginning where you have training. So to also add like an as if or what if loop, so that it's like questioning what it's doing the data that it's taken in each time. It's getting an understanding of what it's doing rather than just mimicking. Same thing with like the neural network.
Right.
Rather than just mimicking that neural network, if it's got some basis to understand why it's mimicking, maybe it would increase the accuracy.
Yeah, okay, so thank you for explaining that again. Yeah, I think a lot of these neural networks was interesting. The more advanced versions, especially if the transformer models they have a sort of proto version of that. So what happens is the machine learning model, takes some input, attempts to produce some output. And this is true of things like the video understanding model too, especially. The machine learning models in general learn from their processes, but the basic model is just like a predictive system. But the way that transformers work, because they have self-attention and cross-attention, they can actually learn from a feedback loop back into the transformer model. So there's a few examples of this out there. The one that I'm trying to think about is how you can connect different architectures together. For example, there are encoders which they have like a certain encoding property, and the encoding property can change if you actually put like a recurrent connection back to the encoder. So what happens is this is like there's another loss process that occurs. There's not only like a training loss, a standard training loss for the model, but there's as you said, loop, right? There's a loop feedback training loss or training step into the model where it kind of like corrects its original objective. So an example is that deep correlational autoencoder has this idea of cross-modal matching function, which I talked about at the previous meetup. That loss function itself is a dynamic loss function, meaning that the loss function adjusts to the learning that the model is doing at any period of time. So it is like learning to correct itself and change its objective. So essentially, as the models improve and as they get more intelligent, they start to mimic self-understanding so that they can correct their own behavior and what they're outputting. So approaching something like human understanding, or understanding in general. But to answer your question, there are models that are set up to do this, have this feedback process. Yeah.
Thank you.
Cool. Any more questions?
So I was going to ask, can you expand on why it fits, like the model fits into your computer? Like LLMs require a lot of memory, right? So why would this have much less memory requirement?
Okay, so for one thing, the models that I demonstrated were connected to smaller models than large language models. The example of the blip model that I set up was connected to a model known as Roberta, which is, if you're familiar with it, it's a model that was pre-GPT, or, well, it was what do you call it? It's co-built along with the same thing as contemporary with GCP. But the model itself still is intelligent enough to generate outputs and more complex captioning, things like that, but it doesn't have all the complex properties of something like GPT. I'm also summarizing here. Large language models are not also, they get more intelligent as they scale, but they don't actually, you don't actually have to scale models as you used to the same level. Like you don't need the same amount of power these days to get the same amount of intelligence. A popular example is the Phi model, for instance. Anyone familiar with Microsoft's? Okay, so that's called a small language model. And that model actually performs, if you're one of those people who looks at the benchmarks, LLM benchmarks, it performs alongside GPT 3.5, but it's like a fraction of the size. So you can actually install these on your machine. You can get a lot of the same weights, because the weights are where the intelligence is stored, the latent space, the embedded space, and you can load that into the model, and it will perform very well at a much smaller data set. And we're learning more and more about how to build these smaller models as time goes on. But you don't even need like a very complex model. Even some of the older models still produce really good text output. So if you connect it with one of these image understanding models, it can mimic, in many cases, what an LLM would output, one of the foundational LLMs. So again, as time goes on, everything gets smaller, including the need to have as much complex intelligence, because a lot of the intelligence that you download in smaller packages can be just as intelligent, just as emergent. So I hope that generally answers your question.
Yeah, thanks. I have another question.
Yes.
I was thinking, so my impression of the future is that, these LLMs, they're going to synthesize all the information together to, but what I mean by that is that like you were going over many examples where humans, when they're looking at a scene, they look at depth, they're trying to understand all the things that you say, the different objects, where they're going, the sound, and they're trying to link everything together. So in the future, do you imagine that this is foundational models are just going to take all of this and they're going to sort of in all of your examples, you're choosing a specific part of the human experience and trying to sort of figure it out. So the large language models of the future, are they going to do all these things and then going to put them together? Does that make sense?
Meaning, are they going to just understand things and put things together as fluidly as people do?
Yeah.
Do things as described?
Is that where it's going?
Yeah. I mean, at this point in time, I think, honestly, if you've seen some of the trade shows that are out there, they're on that verge right now. A lot of the foundational models. I think one of Tesla's trade shows recently demonstrated near instantaneous reaction of robots that were built by Tesla. That were just kind of interacting with the audience. It was more of the robot can immediately respond to a person. It can tell funny jokes. It can interact with multiple people at the same time, and it can do all kinds of tasks where it's manipulating the environment while it's doing all of this, which to me indicates that these systems are essentially verging on human intelligence or human experience in a sense as it is right now. I say not there, obviously, right? But at some point, you cross a boundary where the experience is so much like what a person could experience that you have to ask yourself, is this basically a person? I mean, I don't know. I know that maybe that's a little fantastical, but when you think about it, if you observe what's happening with a lot of these embodied AIs, and especially in robotics, and to me, it's there's. The gap is becoming much smaller. And so to answer your question, yes, I think there will be a point when an LLM can kind of do everything and generalize. Yeah.
Okay, thanks.
I think on the small models, it can be a very good candidate for one of our future talks on the model distillations.
Oh,
For example.
that'd be cool.
We have two questions here, right?
Hello, thank you for the presentation. So I am myself, like you, a software engineer, and I'm not doing AI as much as maybe you do, and I just wanted to ask you a question, depending on what you're doing at your job, how are you training for like all these basic building blocks, I would call it, like you presented as like big building blocks. So myself, when I'm going to implement like an AI feature, I'm going to use like an API at the end. How are you finding time yourself to learn the building blocks pretty much? Like, is it because it's part of your job, are you doing research, or is it just because of your free time you're like doing it? Like, how are you learning? And I'm talking about human learning here.
Oh, sure. Yeah, no, that makes sense. Part of my background is actually in statistical signal processing and proto-AI research. So I actually have like a background in that. Now that's pre-machine learning models in the way that they are now, but I extended some of my understanding and learnings to that domain, to the current domain. And so like things like statistics, the way regression models work, the way autoregressive systems work, I understood already. And so then I just took that into what I'm now doing. And so currently, in staying on the cutting edge of things, it's a combination of things. Part of it is because there's like some of it is my job. Like I have like projects that I work on that are ML related specifically. And in general, a lot of it is also my interest. So I stay on top of a lot of things that are outside of my direct work in AI and ML. And I am doing a lot of prototyping on my free time. So I will put together systems that like, can retrieve stuff, that can play around with images. I'm very fascinated by visual AI and 3D AI and all kinds of AI that relates to like visual understanding. So that's something that I purposefully stay on top of. So I can like see how to maybe build a small version of a system on my own to do those things. And like, so I'm an engineer, so that's like I approach it as an engineer, not as a data scientist necessarily, or not as a a researcher anymore, even though I have a research background. But I just like prototyping with these things, and because those models are now available so ubiquitously, right? Anyone can prototype with these and put things together like Lego blocks and see what happens.
Okay, thank you.
Yeah.
Sorry, I'm just curious with the Wave 2 demo. Do you mind putting in something that's not in the image? So for instance, can we say, where are the couple going? Or why is the man holding a chocolate, for instance? And can we see how does that work?
Yeah, so, sorry, so if I understand your question, it's if you want to the voice, you want to put in a non-English sentence.
No, I'm sorry. In Bleep, the demo you created, the couple were holding hands with balloons.
Sure.
And you asked a question and it would give you an answer. I wonder if you could ask a question that does not, the answer is not in the image. And
Okay.
Yeah, thanks.
Well, if you want to see, sure. Luckily, I have it running already. So
It's like, where are they going? Where are the couple going?
Yeah. So this is a simple version of the model and the thing that it was connected to. So I would say let's not expect much, but let's see. Where are the couple going? To Prague. More than I expected, honestly. Any other questions?
Can you ask one more question?
Yeah.
Can you ask, why is the man holding chocolate?
Okay. Wow, that's bizarre. Because he's a chocolate lover. Okay.
I think we can take one last question.
Could you ask how many windows are in the picture?
All right, let's try it. Many windows in the picture. 4. Well, it didn't get it. Yeah, it's not perfect.
What did he say?
It said 4. It's clearly more than 4 windows there. But yeah, you know, this is
How about
again,
cars?
Cars? Let's see. Cars. No cars. It's not as smart as we thought. No.
How about, is there a car in the picture?
What's that?
Are there any cars in the picture?
Let's see.
I think the county was.
No. Oh, cars. Well, okay, so I don't have an explanation for that, but I can say that if I were to guess, this training set is fairly small that I've trained on. I can extend this set to make a much larger set. This was, again, just for a demo, but you can complexify the model, so maybe it will understand better the more that I add to it. So, yeah.
Okay, so I'm Mariana. Thank you so much for your talk. It was wonderful.
Thank you.
I also wanted to talk about the demos because I'm really impressed with the inference time. I think it's really quick. Like, it's not like usual to see these kinds of answers. And I want to know, like, in such a short time. And I wanted to know, like, have you cherry picked at all, like, what images or function more quickly, or is it just like this model at this size is as quick as that? Because it's really impressive.
Oh, that's cool. I just picked random. I picked random images from the internet. Like I have a bunch of other ones that I can test on as well. Like so, I run this. Again, these are all like just random things. Like. I just picked a picture of coffee beans. And if I ask what's in the image, maybe it's easier to understand. I don't know. Coffee beans. Okay, so it knows that. So again, it's random. I didn't optimize for inference or anything, which is one of the nice things about the book model is that like some of the understanding it has, it's very fast because it's just like its emergent properties and plus attention would make it faster, I guess.
Cool, thank you.
I think we can conclude that part. Thanks so much.